And start share screen. Okay, if you recall, last class, we discussed TensorFlow, okay. So over here, let's take a quick look. So we use graph for TensorFlow. So it can do the parallel processing, can speed up the overall the learning for machine learning. So the basic starting point for our explanation is we assuming like you have this arithmetic operations, and then we can split it into the components here. And with this kind of a range of the components, then we can represent it graphically, okay? And from this graphic, then we can clearly see we can parallel do D and E, okay? So D and E are operations here, and A is also operation. And then with the result of D and E, then we aggregate, okay? And because of this, then we can do parallel calculation. So we can across multiple CPUs or GPUs, so make use of parallel processing, so can expedite the calculation. So like in this case, okay, like in TensorFlow, how are we going to do it? So let's take a look. The corresponding TensorFlow application, okay. And in order to use TensorFlow, you needed to import TensorFlow, okay. And so for TensorFlow, there is a low-level one and high-level one. So we start with the low level, okay? So low level start kind of also building the graph. So let's see. So for that one that we just discussed is it, so over here, so we import the TensorFlow. Okay, and to define the constant like 2.0, that is a constant, is it? Then you just use TensorFlow's constant to define the constant value, okay? Then you assign it to a variable. And for TensorFlow variable, then what you do is you do TensorFlow variable, okay? And here is for that B and C, and you also give the variable name, okay? And for this D is operation, okay? And then you use TensorFlow's add, and then you add what? Add the two variables. Previously you defined B and C, and then you also give this operation a name, okay? Same for E. Okay, then A is multiply D and E, is it? So over here, you define of the variables or constants. So this is starting from very low level, okay? And in order to use TensorFlow, then you also needed to set up the initialization, okay? So to do the initialization, then we can call the global variables initializer. Okay, call this. And then we can start. So for TensorFlow, the low level is you always start, we call it a session to do the operation. Okay, so it's with the session as sessions. Then we first needed to do the initialization. Okay, so this part is to do the initialization. Then you call this session run. And the run what? Run with that operation that we already defined. So A is an operation, okay, not a variable. And then we get the output and we can output the calculated result. So here it shows the calculated result. Okay. So that's regarding TensorFlow to do a very basic arithmetic operation. Okay. In this regard, if you think about it, using TensorFlow to do this looks like it's much more complicated than we just write the regular code. Okay. What next one try to show? Okay. So over here, previously the B and the C, they are variable, but they hold some value, etc. But sometimes the variable may not have value, etc. Then you may use on the fly kind of value, on the go value. So in that case, then you need to define it as a placeholder. Okay, so in this case, variable B is a placeholder, doesn't have any value yet. Okay, and you also define its type and the shape of this variable, and you also give it a name. Okay, and the D and the E the same, etc. And A. Okay, so over here it's just the B part is different. B is a placeholder. And then for this same thing, so each time if we try to use, you need to do the initializer, okay? And then for each of the session, etc. So here, whenever you try to run, it's in a session. So for the sessions, the same thing as previous. You first need to do initialization, etc. Then you run that operation. And with A, that operation, if we recall, B value is unknown as a placeholder, etc. And now we try to fit it with different value. And the value is going to be in range between 0 to 9, etc. So over here, we use a dictionary to feed the value. And the dictionary's key is that placeholder B. Okay, and then in this case, so each time with a value like 0, so this is B is 0, then A is going to be 3, etc. And when B is 1, then A is 6. When B is 2, then it's 9. So it's going to take all of those placeholders value and then do the calculation. Okay, so this shows how we do the placeholder variable. Okay, and what next one try to show as inside and outside of the session if the result are going to be carried. Okay, so here x1, x2 they define as some constant. Then you calculated the result. You can also directly do this, okay? And here's that A is a tensor, okay? And we can also do using the session, etc. And the session, then in this case, you computing in a session, etc. And this session run that result that you just defined, that you just defined. And then we output the result within the session, etc. And here, when you do print this output, this is out of the session, okay, out of the session. But we will still have the result. If you take a look, we still have the result, okay. And then what next to try to do is for a matrix, okay, the matrix. So we already have the value for the matrix, and then you just do matrix multiplication, and you can still run the operation. So this product is an operation. Then we get to the result. Okay. So that's this case. And what next one try to show all the previous discussion not involved with graph yet, is it? So next, let's see. We are going to create a graph, okay? So to create a graph, you can call tf.graph, okay? And then we can do the variable assignment plus the initializer. Then you just define with the graph as default. Okay, then over here, X is a variable placeholder. Okay, and the W is some value, and the B is also some value. Basically, this is what our net input is it for the neural network, the net input. Okay, and then over here, we define the initializer. Okay, and then what next? For the session, then this time, we plug in the graph. Is it? The graph we already defined. Then we plug in with the graph. Then we run the initializer. Okay, and in this case, for the X value, we are going to fit it with different values. Is it? And for each different value, then we will get our net input. Okay, the Z calculated result. Okay, they can. Then in this case, we also get for different values, we get the result. So over here, just to show, you can also define a graph. Okay, and what the next one also try to show the same thing, is it? Okay, and what the next one show is working with array structure. Okay, so here same thing, we still define a TensorFlow graph, and then you kind of define the graph. So graph has some, so X is an array basically here for the shape, is it? And Y, what you do is reshape the previous one, is it? So this is going, depends on the number of values, is it? The shape. And then for this one, it's a reshape. But anyway, the last dimension is going to be 6. The first dimension is going to be whatever based on the previous one, is it? So that's what it defines. And then for this one, it's an operation. Okay, so it's just do the sum of each column. Okay, so do the summation for the column. And then over here to calculate the mean. Okay. Okay, so over there, we already defined the placeholder, the array, and the operation for the graph. And then what next we are going to do is we are going to do the calculation, is it? So now for this array, we are going to assign some values, but the shape is 3, 2, 3. Is it? So basically, we are going to have 18 values, is it? And then for the reshape, if you recall, is it? So first it's going to, so for the session run, you can also see it can be plugged in with different operation, is it? So first one, this X2 is conduct the reshape, is it? And so same thing, we use a dictionary format, okay? And what is the second one is you do the summation, okay? And the third one, you're going to do the mean calculation. So over here, once you have the graph, so what here try to show, once you have the graph, is it when you do the session run, you can run the operation that you defined within the graph, okay? So all of this is just quite arithmetic operation, okay? And what is the next one we are going to explain is we are going to see how neural network, and over here we are going to also use that MNIST data, okay? So let's first get back to the diagram to take a quick look. Okay, so this diagram gave us some idea about how TensorFlow will treat that MNIST. Did we already show that? Screen. Share. Yes. Regarding that MNIST, if you recall, it's 28 by 28, is it? So it's 784 features, is it? So the first, we also need to do the reshape. And the first hidden layer is going to be 300 nodes. Okay, 300 nodes. And if you recall, so basically this part is to do the net input, is it? So Wx plus the bias, okay, to find the net input. This part is for net input, is it? After the net input, then we also do activation. So this operation, so this is the graph for our TensorFlow. So this defines the operation for activation. And for activation over here, we use that rectified linear activation, okay, RELU, okay. So rectified linear unit, okay, rectified linear unit. We're going to use this for the operation. So this is for activation, okay. And then the next layer, we have 10 nodes, is it? And we are going to get also the output for the 10 digits, is it? So this part, we are also going to continue doing, because if you recall, for each node, for each neuron, that you will have the input from the previous layer, okay? So you will have weights from of the previous layer, that, and the input, you need to do the multiplication, that, for the weight, and plus the bias we are going to add, okay? And this layer, we call it logistic layer, okay? And after this, then we are going to generate output, is it? And in the past, if we just do the logistic, do the sigmoid, is it? Sigmoid activation. And over here, after the sigmoid, then we use softmax to do the activation, okay? So this is another kind of activation, softmax. And for sigmoid, so sigmoid is also generate some value, is it, between -1 to 1, is it? And so it's also kind of give us some probability of the probability belong to certain class, is it? So that's regarding the sigmoid. And the softmax has some similarity, but not exact same. They also provide probability. Okay, but over here it's the all probability. If you add them together, the value is 1. Okay, so it will tell you like belong to which class. So belong to which class, the probability is what. But it's when you add all of them together, it's going to be 1. Okay, so that can tell us more information, is it? So that's why over here we use softmax. Okay, and because for neural network, is that we do the gradient descent, if you recall, and we also have the back propagation, is it, to optimize all of the weights. So this part is for the optimization of the weights, is it? For the optimization of the weights, so then we need to consider the cost or loss, is it? So we need to pick some cost function or loss function. Is it? And if you recall previously, we learned like sum of square of arrow is a mean square of arrow. Is it? And for logistic regression, then we can also have that kind of p and log 1 minus p something. Is it? Something like that. So that's all considered as the cost function loss. And the goal is try to minimize that to find the lowest point. Minimize, that's the goal. So over here, we are going to pick, we call it cross entropy. Okay, so this is also for loss calculation. And we are trying to minimize. Okay, and the cross entropy, so it's use the probability and the log of the probability. Okay, and try to minimize. Okay, and then over here we also need to, so we have the cost function that, so we have the gradients, then using the gradient descent to do the training. Okay, so that's the general flow that for, and the graph for the neural network one. Okay, and then let's see the corresponding coding. Okay, and over here we are going to use that MNIST. So this is a handwritten, if you recall, the very classic one. Okay, handwritten single digit. Single digit. Okay, and so over here we got the training data, testing data, and also validation data. Okay, so validation we have 5,000. Then next, let's see how in TensorFlow. But here, be careful. Okay, here we consider low level. And for low level, you can also see it's quite complicated. Is that because we need to define each operation? Is that for the matrix multiplication and addition, and then you need to do that that linear or that ReLU, that activation, and then you also need to do the cross entropy. Oh, not the first cross. It's you also need to do the softmax. And after that, we also need to do cross entropy to minimize. So there are quite a number of operations involved. Okay. So when we do the machine learning, then it involves a number of iterations. So over here, we define, okay, we said we are going to do the 10 epochs. And if you recall, for gradient descent, it's involved learning rate. So here we also define learning rate. And because the data size is quite large, is it? So we are going to do batch. So each batch, we're going to take 100 samples, okay? And then you can see here, we need to do the placeholder for the X and Y for features. And also this is for target value, okay? Okay, so the first layer, we are going to have 300 in hidden layer, okay? So then let's see. So then for the weight size, is it? So weight, the feature, we have 784 input, is it? And the 300 is neurons, okay? And the B is bias term, okay? So that's for the hidden layer. And then we have the next layer is that we have 10 nodes. So you also need to define its weight and the bias, okay? Okay, after we do this, then what next we do is we need to define the operation. So here is matrix multiplication, then addition, and then next, if you recall, is for the activation, we use a rectify linear unit, etc. And its input is the calculated result from the previous layer. And then after that, what we are going to do is we move to the next layer, okay, with W2 and B2, etc. After that, we are going to do softmax activation, okay, softmax. After that, because over here for the softmax, it's the probability. Because probability is between 0 to 1, okay. Between 0 to 1, so it may be 0. But if it is 0, then it may cause some problem when we do gradient descent and the back propagation. Okay, so that's why over here we have a function called clip by value. We do some value clip. Okay, value clip then depends on the softmax calculated result. So the value is going to be, so this is going to be 0, 0, 1. So very small value, but it's not 0. Is it? The larger value is going not to be 1, it's going to be 0.99. Okay. So anyway, so you're going to clip the value, set it between this range, so that later on, when we do the gradient descent training, we won't have the problem, okay? So, okay, after this, then what next we are going to do? So this part is the cross entropy, okay? So for the cross entropy, so basically over here is you're going to do the log operation also with the clipped, okay? And this is 1 minus that, because that's the probability. This is the probability. Okay, so this is the cross entropy. Okay, and then for the after the cross entropy, etc., then we are going to do the gradient descent optimizer. Okay, and then you plug in the learning rate. For the minima is that cross entropy value. Okay. So this is all regarding that diagram. And then what next we are going to do is same thing. You still need to do that global initializer, that global initializer. And the and over here, how we do the correct prediction, etc. So we also needed to find if the real target value and the calculated one the same. So this is going to help us to do the prediction correct or not. And for the accuracy, then we can based on this predicted value to find the accuracy. You can see with all of this, we define each of its operation basically. So it's a node in the graph. Okay. Then what next? We can start the TensorFlow session. Is it for the TensorFlow session? Then over here, like previously, we defined the batch size. Is it? So then the total number of batch based on the data size, etc. And for each iteration, etc. And then for each batch, so this is for each batch, that for each batch, then what we are going to do is we are going to run the gradient descent, that and the cross entropy. Okay, and here the data you're going to get from the training data, but based on, so the batch size is 100. So we're going to do batch by batch, okay? And then finally, we collect the accuracy. Okay, and over here it also gives us each batch's result and the cost. Okay. Okay, and from the calculated result, we can see is that if you take a look at the cost, is it the cost is decreasing? Is it from 0.65 to 0.05? And the accuracy score is also quite high. Okay, so 97%. Okay, and from all this discussion, we can find it's quite a lot of work if we start from scratch to define the TensorFlow graph, etc. But all of the previous discussion is regarding low-level API, TensorFlow API. Okay, so it's quite a lot of work. And TensorFlow also provides us high-level API. So basically, it's from Keras. Okay, so it's called TensorFlow Keras. Okay, so we can use that, and that will save us a lot of work. Okay, so same thing, we're still going to use the MNIST, but this time we're going to get the data from the Keras part. Okay, to get the training and testing data. And the first, we also do normalization, okay, this part. And so for TensorFlow, the high level one, so basically it's the Keras, okay, API. Okay, and the very first step you needed to do is to define the model. Okay, and the model can be, there are two categories. One is sequential, the other is functional. Okay, and for the model, then we are going to configure. So we are going to define the layer for the model, and then we also configure layer. So basically later on we will see this much more simple. It's just define a layer and configure the layer. Okay, and at this point, we are going to take a look at the sequential one. Okay, for the sequential model, it's just a linear stack of layer. So depends on your layer definition. So you just define layer by layer, then you add a layer to the model one by one. Okay, and from input to output. So that's the whole process. Okay. And for the functional model, it's a little bit of more complicated. Okay, so it's said it's connecting output of one layer to the input of another layer. Okay, so it's a little bit of more complicated. So first, let's take a look at the sequential model. Okay, so let's first take a look at the example. And to use the higher level, then what you need to do is you first need to define the model. Define the model, the sequential one, then it from, so TensorFlow, Keras, models, okay, and over here it's sequential. And for the sequential, then this is the first layer, okay. The first layer, if you recall, it's each image, is it? Each image is 28 by 28 pixels. The very first is you need to reshape. And over here, we call it flatten. Okay, so we get the from 2D basically to one dimension, that kind of. Okay, then from 28 by 28 to 784, etc. So this, you just call it a flatten layer. Okay, and what the next one is the hidden layer. Okay, the hidden layer over here, we just have 128 neurons. And you specify the activation is a rectified linear unit. That you can see it's quite simple. We don't need to worry of the others, is it? And later on, we will explain the dropout. Okay. So this is dropout layer. And then the next layer connected to the 10-digit classification. Is it? So we have 10 nodes. So it's also dense layer. Okay, activation is soft max. And over here, dense layer. So dense layer means the input neuron is going to be fully connected to the next layers neuron. Okay, so that's called dense. Okay, dense. Okay, then what is dropout? Okay, so the dropout is to overcome overfitting issue. Okay, and what the idea is, previously when we say the dense is fully connected. Is it? So fully connected means the neurons is going to be connected, fully connected. So the dropout, then it just means, okay, for this neuron connected to this neuron, it will take like 20 probability. So it's not guaranteed to be connected. So that means the weight is maybe 0. Okay, maybe set up to 0 as it doesn't exist. Okay, so then with the dropout added, then your network may not be fully connected. Okay, so then in this case, it can lessen the issue of overfitting. Okay, so first step is we define the model. Okay, so after we define the model, then we can compile the model. Okay, so you need to select the optimizer. Optimizer is the gradient descent training, is it? But there are multiple optimizer, is it? And the Adam one is more efficient, okay, for deep network. And then you also specify the cost or loss method. Is it? Previously, like we said, we use cross entropy. Is it? And here it's defined the sparse categorical cross entropy. It's also efficient. Okay. And this sparse categorical cross is for multi-class classification. Okay, if you have binary classification, then you just do binary cross entropy. Okay, for regression, then you can select mean square error. Okay, and so if we read the documentation, then we will know what we should choose. Okay, so you have a different option. You can also specify your measurement performance matrix. So here we just use the accuracy. Okay, so after you compose, then we can do the fit the model and also do the evaluation. Okay, and for the fit of the model, and here there is some argument called verbose. So what that means is, so for the verbose, you can have 3 settings. Okay, when you set to 0, then it's doing the processing, it's silent. And this is sometimes a bit very annoying, because sometimes when your data size is quite large, it may take quite a while, couple of hours. Okay, that's normal, is it? So then if there is nothing shown, then you may be curious what's going on, is it? So this will not show you anything. Okay, and the verbose one, then it will show animated progress bar. Okay, so this gives you the how it's progressing, is it? And the verbose is 2. Then what it does, it just mention number of epoch. Is it? So better than silent, not as much as the animated. Okay, so that's about the 3 option you can have, is it? So we do fit, then we do the evaluation with our testing data, is it? And we set the verbose here as 2, is it? So we have the ongoing, and it tells us that the time it takes and what the loss is, what the accuracy is. And you can clearly see the loss is decreasing and the accuracy is increasing, is it? And the final result is pretty good, 97%, is it? Okay, so that's regarding that MNIST one, is it? And we explained in both scenarios. And then next, let's take a look. The dropout I already explained, is it? So here again, we are going to use that MNIST, okay? And also over here, you need to import the model you're going to use, like a sequential, is it? And for the layers, a dense, flatten, is the activation dropout. And also over here, it also shows that we can also do normalization and the 2 categorical, is it? And this part previously we already know. So we can do normalization. We can also convert the value, okay? And what the next part to try to show us is for the model, previous one just show us in one statement, is it? But here you can also do multiple statements for the model. So you can first define kind of an empty sequential, then you add one by one, is it? Flatten, add dense, add activation, is it? Dense layer and specify the activation, dense layer specify the activation, is it? You can also get a summary report for your model, okay? Then over here, it gave us the model kind of, detailed view, is it? So for the flattened layer, is it the output shape, is it? And also number of parameters it tells us. So quite a lot of detailed information. And also over here, you can see, is it? I need to draw. The total parameter is quite large, is it? So that's why it's benefit if we do TensorFlow. So after model compile, then you can do model define, you can do compile, specify the loss, optimizer, and the matrix. Okay, so as usual, is it? Then we can do fit, is it, with the training, and also specify number of epochs, the batch size, is it, and the verbose. And for this one, it also gave us the result, okay. And over here it says we can also use plots to diagnose our neural network, okay. So so over here, this history is after we fit our model, is it? After we fit our model, then if you call the history, it's a history, then you can collect its loss and the validation loss also, okay. And then we can do the plotting. And if you recall previously, we discussed about training and validation. So this is not a good one. That's not a good one because it looks like there's some cross over here. And also it shows after the 3rd epoch, basically for validation loss, it didn't change anymore, even though for training one, etc. So this indicates overfitting. Okay, for the training one, looks the result very good. As above, when you do cross validation, it's not good. Okay. And for this model, if we recall previously, we don't have the dropout layer. Okay. And what is the next part? Okay, we can also collect the accuracy and the validation accuracy, etc. And from the we can also say it's overfitting. It's not a good result. And what the next one try to show is we add the dropout layer. Okay, so over here, the first we do the flatten, and then we have the hidden layer. After that, we add the dropout layer. Okay, and after we do activation, we do dropout again. Okay, and then we do the softmax. Is it? So over here we have 2 layers for rectify linear unit, and this is the output. Okay, for the softmax. And normally softmax is used at last layer. Okay, so be careful. It's for last layer, softmax. And we can collect the summary report. And here, then you can do compile, nothing new. And then we do the fit. Okay. So after the fit, then same thing, we can collect the loss and cross validation loss. Okay. And this time we can see for the cross validation, etc. It's not just a stop at epoch 3, etc. And there is no cross between the training and the validation. The validation, the loss is even lower, etc. So this is better. The result shows it's much better. And then we can same thing, collect accuracy and validation accuracy, etc. Then you can see when you do the validation, it's even better, the accuracy, etc. So then the problem of the overfitting. So no overfitting issue. That in this case, this is after we add the dropout layer. Dropout layer. Okay, so that does show can improve the result. Okay. Okay, so that's regarding the examples. And what next one? Previous I forgot to explain the softmax. Okay, so softmax, so basically it does normalize the exponential function. Okay, so after that logic unit, if you recall, is it the logic operation? That part, is it? So then it will do the softmax. So softmax, what it is? So it is a function that takes input with k real numbers, and then does normalize it into probability distribution, still consistent k probability, okay, and to the exponential of the input parameters. And so after we apply softmax, each component, okay, will be in the 0 to 1 interval. But be careful, they will add up to 1. So that's a major part, different from the previous sigmoid. Okay, so the general idea is, so this is the input, is it? So we do the softmax. Okay, softmax. So you do exponential with that value, is it? but over here you add of the, so this is just a proportion of, so the probability, so that's why it's regarding probability distribution. Okay, probability distribution, okay. Okay, so that's regarding softmax, and the clip we already explained, okay. And the cross entropy we also explained, okay. Okay, so so that